All right, let's get started. Hello, everyone. Thanks for coming to this session. And my name is Roy, and I work for Intel on the Edge and ONAP things. So today I'm going to give a presentation. The name is Akraino, EdgeX Core, OpenEdge, ioFog. What's the best solution for your edge? So it's quite a long title. So to give you a brief overview of the, here's the agenda. So we'll first talk about the edge computing definitions. Then we'll talk about the typical edge implementations as well as the features and the use cases. Then we'll talk about the available projects inside the market. And last, we will give out a summary. So first, let's start with the definition of edge computing. I think everyone here should have an understanding about what is edge computing, so just a brief introduction. The edge computing is the placement of data center-grade network compute and storage to be closer to the endpoint device and also closer to the endpoint user. So having this edge computing, we can improve our service capabilities to optimize the total cost of ownership, comply with the data locality, as well as reduce application latency. So we are also having characteristics like this. We may have the low latency and the real-time interactions. We may have the massive data storage and movement, and sometimes we need to enhance security and privacy, and also sometimes the contact or location awareness. Also, you may need some intelligence or smartness on your edge in order to help you with your computation. So just some brief understanding about what is edge computing. Now we're going to implement this. So first talk about some typical implementations of edge computing. I give here 3 implementations which I find from some research. They are fog computing, the mobile or multi-access edge computing, and the third one is called cloud. So let's first go through them one by one from the definitions here. The fog computing is a decentralized computing infrastructure based on fog computing nodes that can be placed at any point of the architecture between the end device and the cloud. So the nodes are heterogeneous in nature, and they can be placed at devices like routers, switches, access points, or gateways, and etc. So for the mobile or multi-access edge computing, we are going to have the point here is it is always residing in the radio access network, and also mainly it's co-located with the network controller or macro base station. So they are running in service to help with the computation and storage here. Okay, the third one is called cloudlet. It is treated as data center in a box running the virtual machines and has the capability of provisioning resources to end devices and users. They are also running in service and with over a one-hop access with high bandwidth as well as low latency. So these are the definitions here. I also summarized the characteristics of these implementations to show some difference between. It's quite obvious, like we're having difference in locations, device, and access mediums. They are somehow related since the fog computing will be placed on routers, switches, access points, or gateways. They're having more protocols supported inside. And also, we are having difference in logical proximity. Since I mentioned for fog computing, this kind of implementation can be placed at any point of the architecture between the end device and the cloud. So there could be one or multiple hoops between the end device and the cloud. And also the ability for near real-time interaction. Here I put the highest for the fog computing since it is nearest to the near-end devices. So that I just assume it could have better ability for near real-time interaction. And also for the multi-tenancy, I think every kind of these implementations would support the multi-tenancy. For the computation power I mentioned here, it is actually some kind of the resource we have for computation. Since the MEC and the CC are running on servers, so most likely there are going to be more resources for the computation. Then the fog computing, they reside on some kind of resource-restrained devices. So there would be, I put a medium here for the computation power. There are also difference on the power consumptions, just related with the computation power I mentioned before. It's also related with the mediums. The MEC are co-located with base stations and network controllers, so it may have more power consumptions, but the fog computing, they are small and they reside on these near-end devices, so it could have less power consumptions. And for the context awareness here, it related to both the environment and also the location things. So the MEC has the highest context awareness since it knows a lot about what mediums have been connected inside, and it has a lot more knowledge about the context around. We are also having difference in coverage, the server density, the cost, traffic continuity, as well as the active users. And you can have all the figures here. So these figures, I also got them from some research, and you can find a reference down. Okay, so we have learned something about these edge implementations. Now, this time we have these implementations, we're going to use it for some kind of edge use cases. So this is an overview of the edge use cases. A pic I get from a survey from McKinsey. You can see that there are use cases everywhere in every industry. We may have it in the transportations, retails, for consumer, for healthcare, every industry, and it's quite promising. It has a potential value of 175 billion to 215 billion by 2025. And in order to have to provide a best implementation for the use cases, here I do a mapping between the characteristics of the edge implementation and the features of use cases. So here in the left part, I choose 8 of the characteristics I mentioned in the previous slide, since they are mostly related with the use case features. And also I put 7 features for the use cases, which are mostly used to measure these use cases inside the research. So you can see that for the access median, it is highly related with the extensibility. Since it could support more protocols, then it could be easier to extend it to different to new devices. And also it could be somehow related with the context awareness. Since more protocols are supported, we are going to have more devices connected inside and provide some context awareness. The ability for near real-time interaction is really highly related with the latency. And for computation power, it is a little bit related with the bandwidth. When we're having more computation powers inside servers, there could be highly more possible that we are going to have more bandwidth. And for context awareness, it really does have impact on context awareness. And for the multi-tenancy and the logical proximity, it could have an impact on the privacy as well as the security, since they have functionalities to do the data isolation, as well as there are less data transportations. It could be easier to manage the privacy and security of the data. And for coverage, some little relationship with the scalability, more coverage, then there could be, the nodes could be distributed to different endpoints and to make it easier for scaling. And for power consumption, it's related to power consumption and also the scalability. So if you need less power, it could be easier for scaling. So after we having that relationship here, we're going to have a little bit deep dive into some typical use cases. I have 7 different use cases here which are having different features. I have the criticals and depends using different colors here. And due to the time restriction, I'm going to choose one, for example. So let's take the smart cities as an example. It has the requirement or features it needs for the latency, extensibility, and scalability. And also it has some requirements for bandwidth, context awareness, power consumption, as well as the privacy and security. After we know these requirements, we're going to use this workflow to find the best edge implementations. We put the use case features inside and find a related implementation characteristic. Then it will tell us what the appropriate edge implementation would be. So actually for smart cities, as I mentioned, it needs the latency, the scalability, and the extensibility. So as we mentioned, the extensibility is highly related with the access mediums, and also we have the latency related to the ability for near time interaction. So here I put the recommendations as the fog computing implementation plus the MEC implementation. Since these two, they're combining together, will provide a perfect solution for the smart city use case that matches every feature or requirement that I mentioned before. Okay, so for the other use cases, I'm also giving out these recommendations. So you can take a look later. I'm using the same workflow to map it through into the implementation I've mentioned before. So the next, we're going to talk about the project. There are so many projects are targeting on Edge. So this time we're still using the same workflow, but we're putting the projects here within the Edge implementations. So after we have this understanding about Edge implementations, we're going to categorize these projects into different implementations and make them to be suitable for Edge use cases. So you can see a lot more projects here. Every word here is a project name that's targeting on Edge. So I'm just going to talk about 9 or 10 of them due to the time restriction. So let's first go to the first one. It's the Akraino Edge Stack. I think most of you should be familiar with this one. It's a project inside the Linux Foundation, and it's a fully integrated edge infrastructure. It intends to develop solutions and support of carrier, provider, and IoT networks. So it's really an integration project. You can see from the architecture, it has almost every layer that you need for an edge solution. It has the part for the edge platform software, has the part for NV orchestration, edge applications and orchestration, as well as these APIs and GUI interfaces. I also put some examples here in the white box, like the projects that can be used in this layer. You can see that it could use the OpenStack or Kubernetes as the infra orchestration and use Ceph as the storage. So since it's a integration project, and I'm not going to refer it to any kind of implementation I've mentioned before, and I'm going to show about the blueprints within the project. You can see that the list here are the projects has been approved by the community, and you can see that it covers almost every scope that you have for Edge. It has the connected vehicle, it has the video processing, it has blueprints on radio edge cloud, has the part on time critical edge compute, so it's really covering every area inside Edge. Okay, the next project I'm going to talk about is Airship. I think many of you have heard presentations about this project during the summit, and I'm not going to go deep inside since there are a lot more presentations to talk about these updates or onboarding of this project. So for here, what I have is it's a declarative YAML-driven deployment tool, and it's also helping with the lifecycle management of the infrastructure. So first, in the first time, it's trying to give out implementation of OpenStack on Kubernetes, and it's now, according to the updates from in the summit, it's also going to support other platforms based on Kubernetes to using the other Helm charts. And every block here in brown are the components of Airship. They're having different functionalities. Some of them are doing the to bootstrap the Kubernetes, and some of them are working for the configuration files. And I'm not going to go deep inside, but there's one component called the MADA, which is used to help with the complicated Helm chart deployment. And it can help, the Airship project can help you bootstrap the undercloud infrastructure and build the OpenStack platform on it. And it also has been evaluated by several companies. It has been evaluated by AT&T themselves, as well as Ericsson, SK Telecom. They're all using this project as part of their framework or tested in their lab. I'm not going to refer to any kind of implementation I've mentioned before either, since you will need it once you have a requirement for deployment. And the third one, okay, the presentation before they just have an introduction on Starling X, and it's led by Wind River and Intel, and it's a deployment-ready, scalable, and highly reliable edge infrastructure software platform. So we all know that it is a platform based on OpenStack, but not limited to that. It has some special services inside the layer, the Flock layer. We have a lot more management to take over the work from the users to help improve the low-touch manageability as well as the reliability. Also, we are having this project is a conversion of the containerization as well as the virtualization. We are having these Kubernetes, actually it's using one-off component in Airship called Amara to have the Kubernetes built inside and have the OpenStack platform built up. And you can see that in the controller node, we're going to have the containers for OpenStack platform, and then inside the worker node, we're going to have the application VMs on the OpenStack platform. And here I've also have a figure here to talk about the features of this project. So it's a project covering both the MEC and CC implementation. Since it is running on servers, and it can be deployed in the base stations. It has somehow a little bit more computation power since when it is deployed on the base stations. And it supports the multi-tenancy since it is using OpenStack. Also for the ability for near real-time interaction, I put it a lower here because it is running servers. So here I just say it's a project that covers both the MEC and CC. I'm also going to talk about the evaluation of Starling X. Since I'm based in China, I'm going to provide some information that what the Chinese companies are interested in the Starling X. So you can see that we have China Unicom together with Intel and Atlantic Cloud build a new MEIAS service based on Starling X. And we are also having two Akraino blueprints we've mentioned before before, one proposed by Tencent on the connected vehicle, the other one proposed by Wind River on far edge distributed cloud. They're both putting Starling X as a component inside. And the China Mobile Suzhou Software, as well as the China Telecom Research Institute Guangzhou, have also evaluated Starling X as a component or a potential platform they're going to use for their edge or cloud. And we are also having the China Mobile Research Institute and Intel together experimented the VCP onboarding on top of ONNAP with Starling X. Okay, the next project here is called CORD. It's the abbreviation of Central Office Re-architectured as Data Center. So it's obvious like it's managing the data centers while using declarative modeling language for agile real-time configuration of new customer services. And it's a virtualized service delivery platform to provide both cloud economics as well as the agility. And to take a look inside the inner service architecture, you can see that it is really everything as a service. We're having ONNAS as the SDN, which is implemented by service and also used by service like OpenStack. And we're having XOS working as the controller plane for the whole project, but also implemented by several services. And this is a framework that this attempt to help users to fulfill the needs of subscribers from any scope whatever it's from residential, enterprise, or mobile. So it's really a typical MEC implementation. It has the more computation power, but not that much access medium listed here, and a lot more context awareness, and also the coverage is good since you can find base stations everywhere in our city. Okay, the next project here is called VCO, the Virtual Central Office, a similar one with CORD. They're having almost the same purpose to have a virtualized central office. And it's a POC only, has completed 2 demos on residential, enterprise, and mobile services. And as far as I know, they're going to give out the 3rd demo recently. The difference here is that it's using ODL as the SDN controller and using ONNAP as the NFV orchestrator. So it's another typical MEC implementation. The 5th project here is EdgeX Foundry. I think it's a well-known project for IoT services. It's a loosely coupled microservice framework with device management and various protocols supported. You can see that it has clear architecture, 4 layers. Each have their different functionalities from the southbound to the northbound. In the end, we have the device service, which providing several protocols. You can see there are SMTP, MQTT, ZigBee inside to connect with different devices here. And we have the core service, which first handles with the data, stored inside, and also it stores the metadata and have the commands we can process here. In the supporting service, it is responsible for the routings and the scheduling, and you can also write your own microservice and insert it here for computation purpose. The export service is the part where you're going to register as a client of this platform so that you can get the information from the end device. Like what I said, the figure here shows that it has the multi-tenancy part through some. Oh my God! It has the multi-tenancy ability, and it has less power consumption since it can be run inside gateways and routers, and there are true use cases. They are run in Raspberry Pis. And also we are having less coverage since they're just going to cover a small area for the devices. And we are also having a lot more access mediums here since inside the device service, we're supporting multiple protocols. So here I just refer it to a kind of typical fog computing implementation. The sixth project here is called OpenEdge. I think maybe you're not familiar with this one since it is a project that open sourced by a Chinese tech company called Baidu, and it is a computing framework that provides temporally offline low latency services and to have functions like remote synchronization, video pre-processing, and AI inference, and etc. So you can see there are two parts in this project, the master as well as the services. The master is the part where handles the start, stop, and wait of the services. And we have 4 services here. The first one is the agent. The agent is the one going to talk with the cloud management suite, which is a part reside inside the cloud. And it is the part does the remote synchronization as well as the configuration updates. And second, we're having the OpenEdge Remote MQTT service. It is a MQTT broker that's talking to the remote IoT hub. Here, it now supports the AWS IoT hub as well as Baidu's own IoT hub. And it can also talk to other MQTT brokers. And we're having the third service is the OpenEdge Hub. The OpenEdge Hub is like a message bus to talk with, to communicate between the functions and the remote MQTT service. And it can also talk to remote external devices. And I think the merit for this project is that it has a function already supported inside. It has a module supported for the Python 27, and you can use these modules to write your own microservice for computation, and also have your function runtime instance there. And for the services, it supports both the containerization mode and the normal process mode. You can deploy it through Docker, and you can also have it in just like normal processes. For the features here, it can be reside on small devices or near-end devices like gateways or routers, and has more access medium since it has the MQTT protocols here. And for the logical proximity, there could be multiple hubs between the end device and the cloud. So here I also refer it as a kind of typical fog computing implementation. The next one is called KubeEdge, another project that open sourced by Chinese giant tech company, Huawei, and it is a project under the CNCF Foundation. It is the first Kubernetes native edge computing platform. As you can see, it has 2 parts: the cloud part and the edge part. The cloud part is where it does the synchronization and get the updates from the edge side. And for the edge part, it's more like a remote Kubernetes node with more functionalities. You can see that it has hubs, it has some service bus and event bus to talk with external services and remote and external devices through MQTT broker. And it also has the function of device management through the device tooling, and has the metadata stored inside the meta manager. For the edge, the component here is just like what we have for the Kubernetes node. It has port inside, has the stateful sets and the config maps, and you have your own containers and your own microservice inside this component. So this project has provided some solid statistics, like it has more footprint, it needs just 66 megabyte and nearly 30 megabyte for memory. And it's saying that it's easy to enable a mini cloud and edge. So for the figures here, I'm also going to make it a typical fog computing, which has more access mediums and less coverage. And for the multi-tenancy here, since it's based on Kubernetes, and there's no solid definitions for multi-tenancy in Kubernetes, so there's no a clear definition for the multi-tenancy in this project either. So this will be the last project, the ioFog. It is a project within the Eclipse Foundation. It is the project with the simplest architecture. It is trying to deploy, run, and network the distributed microservice at edge, and it has only 3 components here: agent, controller, and the connector. The agent is a daemon service that is responsible for the microservice inside the node, and the controller is the one who does the orchestration and manage these agents. And the connector is even an optional component. You will only need it once you want communication between the nodes. Since it's quite simple architecture, so you need to write a lot more code yourself to have these routing, schedulings, and computations with your own microservices. So here I also have this about the same features as what fog computing does, but for the multi-tenancy part, since it has no functions like this, so I just put a 1 for it. And I'm also referring to a typical fog computing implementation. So due to time restrictions, I'm not going to talk more about the projects, but I will have 2 more slides for information for reference. I will put these segment focus, the infrastructure, the code repos, as well as the key participators here to give you some extra information. There are 2 pages about 11 projects. So I think it should be the time now. We're going to, go back to the previous slide. So it's time for summary. We have learned that, according to the previous talk, we have learned that there are different edge computing implementations, and they have difference in characteristics, and the use cases are also having different features and suitable implementations according to these features. And also we can categorize these projects into different implementations. So the summary here is you should first take a good look in your edge use case and find the features according to the metrics maybe the metrics I put in the previous slide, and also use these mapping to find a appropriate edge implementation, and then you can choose the project to deploy it. So I hope this talk will help to inspire or guide you to find a good solution for edge. That's all. Thank you. So any questions?
Out of these projects, which one would you consider a bit more mature?
Oh, it's a hard question, right? You want me to really compare about these projects, but they are having different features and they're having different platforms. If you want to have some, they're on different layers, and if you want to have some for the PaaS layer, maybe, then you have a cluster in OpenStack, or take an example, OpenStack, then you may choose things like OpenFork or the EdgeX Foundry. They are all fine, and they are mostly loosely coupled. You can have your own microservice inside. And if you are having a Kubernetes cluster, then you should have the KubeEdge to help you with your edge computation. So it really depends on. Any other questions? If no other questions, Thank you. Thank you for coming again.